And now in this lecture I will answer two questions. In the first question we find out the area of this green shape that is inside square TPQS, and in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have two squares. We have the big square TSQP. This is the small square ABCP. In addition, we know that this is polygonal MPCP that is equals to 27 square units inside, and this is triangle AMP that is equals to 9 square units in its sides. Again, our test is to find out the area of this green shape. So first of all, we know that the area of this square ABCP in total is equal to 27 plus 9, that is 36 square units in its sides. So writing down the area of the small square ABCP is equal to 36 square units in its size. Again, the area of this square ABCP is equal to 36 square units in size from one side, but from the other side, we know that the area of any square equals to the length of one side squared, and therefore the area of this square ABCP will be equal to the length of side AP squared. That is AP squared. But again, from one side, the area of the small square ABCP is equal to 36 square units in size, but from the other side is also equals to AP square. From this equation, AP square equals to the area of the small square ABCP equals to 36. We will derive that AP square equals to 36. So AP square equals to 36. Here we'll take a root out of this equation, and finally we get that AP equals to the square root of 36, that is 6. This is side AP is equals to 6 units in its length. Equals to 6 units in its length. We know that all the angles inside the square are right angles. So in square ABCP, this angle is a right angle. And therefore, triangle AMP is a right angle. This is the right angle, triangle AMP. So we note that the area of this right triangle equals to 9 square units in its size, according to what is given in the question from one side. But from the other side, the area of this right triangle AMP equals to the base AM times the height AP over 2. Repeat again, from one side, the area of the right triangle AMP equals to 9 square units inside according to what is given in the question, but from the other side, the area of one triangle equals to the base, that is AM, times the height AP over 2. From this equation, AM equals to AP equals to 2, equals to the area of the right triangle AMP equals to 9. We derive that AM times AP over 2 equals to 9. AP equals to 6, so we substitute AP by 6 and we get that 6 times AM over 2 equals to 9. Six over 2 is 3, so total this expression equals to 3 times AM equals to 9. Here we divide this equation by 3. And finally we get that AM equals to 9 over 3 is 3. So AM equals to 3 units in its length. This is side AM that is equals to 3 units in its length. In the next step, we'll implement the Pythagoras theorem on this right triangle AMP in order to find out the length of the hypotenuse AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy the right triangle AMP in the new page and we'll implement on it the Pythagoras theorem. Here by PT is a version for Pythagoras theorem. So finally, this is the right triangle AMP that the curve from the drawing. In this right triangle AMP, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP squared equals to AM squared plus AP squared. MP is the missing side, so we'll leave it as it is. So it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total we should find out that MP squared equals to 9 plus 36, that is 45. So MP squared equals to 45. Here we substitute 45 by 9 times 5 and get that MP squared equals to 9 times 5. Here we take a root out of this equation. Finally we get that the missing hypotenuse MP is equal to the square root of 9, that is 3, so inside the root we left only 5. So in total we should find out that the left of side MP, the hypotenuse MP equals to 3 times root 5 units in its length. This is side MP. Is equals to 3 times quarter 5 minutes in its length. You know that all the angles inside in the square are right angles. So in the big square TSQP, this angle is a right angle. Those two angles are defined as vertex angles, so we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rules I mentioned. Vertex angles are equal to each other. So in the big right angle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. That is to say, 90 degrees minus alpha plus alpha is 90 degrees, 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the small right triangle TBM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha, according to the sum rule that said that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right angles are similar to each other according to angle similarity rule. We'll explain anyway why those two right angles are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the three angles of the big right triangle A and P are correspondingly equal to all the three angles of this right small triangle T and B, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. We actually found out that the big right triangle A and P is similar. This is the sign of similar to the small right triangle T and B according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. Okay, again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. So in the next step, we find out the length of this line segment MB. From the drawing, it is very easy to see that MB equals to AB minus AM. MB equals to AB minus AM. We know that all the sides of this small square ABCP are equal to each other. AP is 6, therefore AB is also 6. So MB equals to AB, that is 6, minus AM is 3. So in total, MB equals to 6 minus 3, that is 3. MB equals to 3 units in its there. This is side MB, that equals to 3 units in its there. So if you found out that for the fact that those two right angles are similar to each other, the following relationship exists between their sides. AP over TB equals to AM over TM equals to MP over MB. AP is 6 over TB. TB is the missing side, so leave it as it is. And it is equal to AM. AM equals to 3 over TM. TM is the missing side, so leave it as it is. And it is equal to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we should find out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. And we left only with square root of 5. So in total, we should find out that 6 over TB equals to 3 over TM equals to square root of 5. Repeat again, we should find out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two sides are equal to each other, therefore you get the present equation from those two sides that are equal to each other. So you get that 3 over TM equals to the square root of 5. Here we multiply this equation by TM and then we divide it by square root of 5 and we get that the missing side TM is equal to 3 over square root of 5. This is the missing side TM is equal to 3 over square root of 5 units in its length. Likewise, those two sides are also equal to each other, and therefore we get the second equation from those two sides that are equal to each other. That is to say, 6 over TB equals to the square root of 5. Here we will multiply this equation by TB and then we divide it by square root of 5. And finally we get that TB equals to 6 over square root of 5 units in its length. This is the missing side TB that equals to 6 over square root of 5 units in its length. Our task is to find out the area of this green shape. So, what is the area of the green shape? On the drawing, it is very easy to see that the area of this green shape will be equal to the area of the big square TSQP, minus the area of this quadrilateral MBCP minus the area of this small right triangle TBM. So write it down. The area of this green shape in total equals to the area of the big square TSQP minus the area of this quadrilateral MBCP. This equals to 27 square units in its size according to what is given as the question. Minus the area of this small right triangle TMB. And again, I have found out that the area of this green shape is equal to the area of the big square TSQP minus the area of quadrilateral MBCP. It is given as the question that the area of this quadrilateral MBCP is equal to 27 square units in its size minus the area of this small right triangle TBM. Minus the area of the small right triangle TBM. First of all, we have to find out the length of side TP of the big square TSQP. So what is the length of TP? From now it is very easy to see that TP in total equals to TP plus MP. Again, TP equals to TM plus MP. And again, TP equals to TM plus MP. So TP equals to TM, TM is 4 over 4 to 5. Plus MP, MP is 3 times 4 to 5. So in total, if you want to know that TP equals to TM, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. So TP in total equals to TM, that is 3 over square root of 5. And we have here 3 times square root of 5, so we multiply this number by square root of 5. And then we divide it by square root of 5 in order to have a common factor in this number. Square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, the numerator of this expression we have 15, and we have to divide it by square root of 5. So in total, TP equals to 3 times 15, that is 18, over square root of 5 units in its name. So if you found out that TP equals to 18 over square root of 5 units in its name. This is side TP, that is equals to 18 over square root of 5 units in its name. So we already found out that the area of the green shape is equal to the area of the big square TSQP minus the area of quadrilateral MBCP. This is equal to 27 square units inside according to what is given as the question, minus the area of the right small triangle TMB. And again, we already found out that the area that we are looking for in this question, this is the area of the green shape. So that is equal to the area of the big square TSQP minus There of quadrangle MBCP that is equals to 27 square units inside, minus there of the small right triangle TMB that we have to find out its area. We know that the area of this square TSQP equals to the length of one side. We take side TP squared. So the area of this big square TSQP equals to TP squared. Minus the area of this quadrangle MBCP, this is equals to 27 square units in size according to what is given as the question, so it is minus 27 minus the area of this right triangle TMB. The area of this right triangle TMB equals to the base TB times the height TM over 2. And again, the area of the small right triangle TMB equals to the base TB times the height TM over 2. So what is the area of the big square TSQP? The area of this big square TSQP equals to TP squared. We already found out that the length of side TP is 18 over square root of 5 units in its length. Therefore, the area of this big square TSQP will be equal to 18 over square root of 5 squared. That is TP squared. Minus the area of quadrangle MBCP, that is equals to 27 square units, minus the area of the small right triangle TMB, that is equals to the base TB. The base TB equals to 6 over square root of 5 times the height TM, that is 3 times square root of 5, divided by 2. So the area of the big square TSQP equals to 18 over square root of 5 squared. 18 over square root of 5 squared equals to 18 squared, that is 324, over square root of 5 squared, that is 5. So in total, the area of the big square TSQP equals to 324 over 5 square units in its size. Minus the area of quadrangle MBCP, that is 27, minus the area of the smaller right triangle TMB, this equals to, here we have in the numerator of 6 times 3 is 18, over square root of 5 times square root of 5 is 5, and square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small triangle TMB equals to 18 over 10 square units in its size. So we have here 324 over 5, that is 64.8 minus 27 minus 18 over 10. 18 over 10 is minus 1.8. So it is minus 1.8. So we have 64.8 minus 1.8 is 63. So in total this number equals to 63 minus 27. 63 minus 27 is 36 square units. So if I found out that if you are looking for this question, that is the area of this green shape, in total it is equal to 36 square units in size. So finish with the first question. In the next step, I'll present you the second question and we'll solve the second question in the next lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have a square ABCD. We know that one side of square ABCD equals to 10 units in its length. Therefore, all the other sides also equal to 10. In addition, inside this square ABCD, we have this semicircle. We know that the diameter BC of the semicircle is 10. We'll define the center of this semicircle. This point is point O. If the diameter is 10, it means the radius must be equal to 10 over 2, that is 5. So the radius OB is 5, and the radius OC is also 5. And we have also this big quarter circle. We know that the center of the quarter circle is at point A. Point B is a point on the quarter circle. Point B is a point on the quarter circle itself. So therefore, AB is the radius of the quarter circle, that is equals to 10. In the next step, we define the intersection point between this quarter circle and this semicircle. This point is point M. And we join points A and M together by step 9. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle, is equals to 10 units in its length. AM is also a tangent to the semicircle at point M. AM, line segment AM, is also a tangent to this semicircle at point M. In the next step, we will join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, and therefore OM is the radius of the semicircle, is equals to 5. So here we can implement rule 1. Now drawing, we have the radius OM of the semicircle, that is equal to 5. It is drawn to point M, that is the point of tendency of tangent AM in this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO according to rule 1. If AM is perpendicular to MO, it means that this angle is a right angle. We know that all the angles inside the square are right angles, so in the big square ABCD, this is a right angle. In the next step, we'll join points A and O together by a straight line. By joining points A and O together, those two right angles. This is the right angle AMO, this is the right angle ABO. So, in the next step, we'll prove that those two right angles can go into each other according to side rule. And again, we'll prove that those two right angles can go into each other according to side rule. So, why those two right angles can go into each other? First of all, side VO of the right angle ABO equals to side OM of the right angle AMO. They are both the area of the semicircle, that is equals to 5, and therefore they are equal to each other. So, and it's on. Meaning again, we found out that side OB of the right triangle ABO equals to side OM of the right triangle AOM. They are both the radii of the semicircle is equals to 5, and therefore they are equal to each other. Likewise, side AB on the right triangle ABO equals to side AM on the right triangle AOM. They are both the radii of the quarter circle that is equals to 10, and therefore they are equal to each other. So AB equals to AM. And again, if we found out that side AB of the right triangle AOB equals to side AM of the right triangle AOM, they are both the radii of the quarter circle that is equals to 10, and therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles, so we can write down that AO equals to itself is a common side that belongs to both triangles. So if we found out that all the triangles of this right triangle ABO corresponding equal to all the triangles of this right triangle AOM, and therefore those two right triangles can go into each other according to side rule. So write it down. If we found out that the right triangle ABO converge, this is the side converge to the right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two angles can go into each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles and congruent triangles are equal to each other. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. We know that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABO, alpha plus beta plus 90 degrees must be equal to 180 degrees. But again, in the right triangle ABO, the sum of the angles must be equal to 180 degrees. That's to say, alpha plus beta plus 90 degrees, in total must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and you get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and you get that beta equals to 90 degrees minus alpha. In the next step, we'll implement the Pythagoras theorem on this right triangle ABO. So we copy the right triangle ABO in an equation. We will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression of Pythagoras theorem. So first, this is the right triangle ABO that are coming from the original drawing. This right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so limit is it is, so it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, it is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, it is 25. So in total, if you found out that AO squared equals to 100 plus 25, 100 plus 25 is 125. So AO squared equals to 125. Here we substitute 125 by 25 times 5 and we get that AO squared equals to 25 times 5. Here we take a root out of this equation and finally we get that the missing hypotenuse AO is equal to the square root of 25 is 5, so inside the root we left only 5. So in total we found out that AO equals to 5 times root of 5 units in its name. This is AO that equals to 5 times root of 5 units in its name. So we continue to focus on the right triangle ABO. In the right triangle ABO, sinus alpha equals to BO over AO. The right triangle ABO, sinus alpha equals to BO over AO. BO is 5 over AO. AO is 5 times root of 5. So in total, sinus alpha equals to 5 over 5 times root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled. And we left only with 1 over root of 5. So in total we should find out that sinus alpha equals to 1 over root of 5. Our task is to find out the size of angle alpha itself. In order to find out the size of angle alpha, we'll operate the opposite function of sine, that is arc sine of the result of sinus alpha, that is 1 over square root of 5. This way we get the value of angle alpha itself. So arc sine of 1 over square root of 5 equals to alpha. And arc sine of 1 over square root of 5 is equal to 26.565 degrees. And therefore, angle alpha equals to 26.565 degrees. And therefore, 2 alpha equals to 2 times 26.565 is actually 53.13 degrees. This is angle MAB, this equals to 2 alpha, and 2 alpha equals to 53.13 degrees. We already found out that beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. We already found out that alpha equals to 26.565 degrees. So in total, beta equals to 90 degrees minus 26.565 degrees. This actually equals to 63.345 degrees. So beta equals to 63.345 degrees, and therefore 2 beta will be equal to 126.87 degrees in its size. 126.87 degrees in its size. This is angle 2 beta, this is angle MOB, and it is equal to 126.87 degrees in its size. Our task is to find out the area of this green shape. In order to find out the area of this green shape, we join points M and B together by a straight line. By joining points M and B, we divided the green shape into 2 parts. The first part is the upper segment, and the second part is the lower segment. We define this upper segment as segment MUB, and we define this lower segment as segment MLB. We'll find out the area of each segment separately, and then we'll add the 2 areas of each other, and this will give us the area of this green shape. So first of all, we'll find out the area of this lower segment MLB. In order to find out the area of this lower segment MLB, I'll copy this sector ABM in an Olympiad. We will analyze this sector ABM. briefly, this is sector ABM that are coming from the original drawing. So, first of all, what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. This is sector A or B. You can see that it is a portion of this circle that is enclosed by two radii, the other end of the circle, and arc AB between those two radii. The two radii are defined as the legs of the sector, and the angle theta is the angle is located between those two legs of the sector. And the area of this sector AOB equals to pi r squared. That is the area of the circle that contains the sector. R is the radius of the circle, times angle theta, that is the angle between the legs of the sector, over 360 degrees. So repeat again, a sector is a portion of a circle enclosed by two radii and the arc between them, and the area of a sector equals to pi r squared, that is the area of the circle that contains the sector, times angle theta, that is the angle between the legs of the sector, over 360 degrees. So it is pi r squared times theta over 360 degrees. So use the new formula in order to find out the area of this sector, sector A and B. The rounded side above ABM is the sign of a sector. It is sector ABM. We already found out that this is angle to alpha, that is equals to 53.13 degrees in size. So the angle between the legs of the sector is 53.13 degrees. The two legs A, B, and AM, A, B, and AM, they are both the radii of the quarter circle, that is equal to 10. So AB equals to 10. AM also equals to 10. According to the formula that I presented to you, the area of this sector ABM will be equal to pi r squared. That is the area of the circle that contains the sector, times theta, that is the angle that is located between the legs of the sector, and theta is 53.13 degrees over 360 degrees. The radius r is 10, therefore r squared is 100, 10 squared is 100, so in total pi r squared is 100 pi times 53.13 degrees over 360 degrees. So in total, the value of this expression, 100 pi times 53.13 over 360 degrees, in total it is equal to 46.3646 coordinates in size. 46.3646 coordinates in size. Now this sector ABM equals to 46.3646 coordinates in size. Our test is to find out the area of the lower segment BLM, the area of this lower segment BLM. So what is the area of the lower segment BLM? This is the lower segment BLM, that I quote from here. This is the lower segment BLM from the original drawing. So, what is the area of this lower segment BLM? From the drawings, it's very easy to see that the area of this segment BLM equals to the area of the big sector ABM minus the area of triangle ABM. So if you know the area of the lower segment BLM is equal to the area of the big sector ABM this is sector ABM. We already found out that the area of sector ABM equals to 46.3646 coordinates in size minus the area of triangle ABM. Side AB of triangle ABM equals to 10 units. Side AM also equals to 10. And then between side AB and side AM is 53.13. So we have to find out the area of this triangle ABM. In order to find out the area of this triangle ABM, I'll present to you a new formula that will help us to find out the area of any triangle. This is triangle ABC that could be any triangle. In triangle ABC, side AB equals to A unit in itself, side AC equals to B unit in itself, and the angle between side AB and side AC is theta. So in this triangle ABC that could be any triangle, this triangle will be equal to A times B times sinus theta over 2. So this triangle ABC equals to the multiplication of two sides by each other times sinus angle between those two sides, that is sinus theta over 2. So we use the new formula in order to find out the area of this triangle ABM. According to the new formula that I presented to you, the area of this triangle ABM will be equal to AB times AM. That is the multiplication of two sides by each other times the angle between those two sides, that is times sinus angle between those two sides, that is 53.13 degrees. So it is sinus 53.13 degrees over 2. That is the area of this triangle ABM. AB is 10, AM is also 10. 10 times 10 is 100, divided by 2 times sinus 53.13. Sinus 53.13 is equal to 0.8. So total we found out that this triangle ABM equals to 100 over 2 is 50, and 50 times 0.8 is 40. So in total we found out that the area of this triangle ABM equals to 40 square meters in its size. And the area of this lower segment BLM equals to the area of sector ABM, that is equal to 46.36 square meters in size, minus the area of this triangle ABM, that is 40 square meters. It is very easy to see that if you remove from this sector this triangle, you will get segment BLM. Therefore, the area of segment BLM will be equal to the area of this sector minus the area of the triangle. Because if you remove the triangle from the sector ABM, we get segment BLM. So in total, the area of segment BLM equals to 46.3646 units minus the area of this triangle ABM, that is 40. 46.3646 minus 40 equals to 6.3646. 6.3646 units in size. So in total, you should find out that the area of this lower segment BLM is equal to 6.3646 square meters in size. In the next step, you have to find out the area of this upper segment BOM. In order to find out the area of this upper segment BOM, I'll copy this sector BOM and then open it in another this sector. So actually, this is sector BOM that are coming from the original drawing. This sector BOM, angle BOM, this is angle BOM, this is angle BOM, this is equals to 2 beta, and 2 beta equals to 126.87 degrees inside. So angle BOM equals to 126.87 degrees inside. BO equals to OM, BO equals to OM, they're both the radius of the semicircle is equals to 5. So BO equals to 5, OM also equals to 5. According to the formula that I presented to you a couple of minutes ago, the area of this sector BOM must be equal to the area of the circle that contains the sector, that is pi r squared, r is 5, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. So in total, if you wonder that the area of this sector BOM equals to pi r squared times 126.87 degrees over 360 degrees. R is 5, therefore r squared is 5 squared is 25, so pi r squared is 25 pi times 126.87 degrees over 360 degrees. In total, the value of this expression, 25 pi times 126.87 over 360 degrees, in total, this expression equals to 27.67 square meters in size. 27.678 square meters in size. So the area of this sector BOM is equal to 27.678 square meters in size. Our task is to find out the area of this upper segment BUM. So what is the area of this upper segment BUM? Actually, it is very easy to see from the drawing that if you remove from this sector BUM this triangle BUM, you will get segment BLM. Segment BUM. The green segment BUM. So the area of the upper segment BUM this is the upper segment BUM. It is equal to the area of the big sector BOM. is sector BOM minus the area of triangle BOM. Minus the area of triangle BOM. BO equals to OM equals to 5. And the angle between BO and OM is 126.67. It is 126.87 degrees in its size. 126.87 degrees. We already found out that the area of sector BOM equals to 27.678 degrees in its equivalent in size minus the area of this triangle BOM. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM will be equal to BO times OM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is 126.87 degrees, over 2. BO is 5, OM is also 5, so BO times OM is 5 times 5, this is 25. Sinus 186.87 degrees is 0.8 divided by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is equal to 10. So in total, we should find out that the area of this triangle BOM is equal to 10 square units in its size, and therefore the area of this upper segment BOM will be equal to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10. 27.678 minus 10 is 17.678 degrees in its size, square units in its size. So the area of this upper segment BOM equals to 17.678 square units in its size. So the area of this upper segment BOM is equal to 17.678 square units in its size. And therefore, the area of this green shape equals to the area of the upper segment BOM, that is 17.678, plus the area of this lower segment BLM, that is 6.3646 square units in its size. So in order to find out that the area of this green shape is equal to the area of the upper segment BOM, that is 17.678, plus the area of the lower segment BLM, that equals to 6.3646 square units in size. And therefore, the area of this green shape, in total it is equal to 17.678 plus 6.3646, that is actually 24.0426 square units in size. And again, we should found out that the area that we are looking for in this question, that is the area of this green shape, in total it is equal to 24.0426 square units in its size. So I finished with the second question. In the next step, I'm starting with the lecture. We'll start with the first question, of course. In the first question, our test is to find out the area of this ring shape. So, in the domain we have two squares. This is the big square TSQP, and this is the small square ABCP. And in addition, we know that this is quadrilateral MBCP. This equals to 27 square units inside, and this is triangle AMP. This equals to 9 square units inside. Our task is to find out the area of this ring shape. So first of all, we know that the area of this small square ABCP in total it is equals to 27 plus 9, that is 36 square units in size. And again, the area of the small square ABCP in total it is equal to 36 square units in size, but this is from one side, but from the other side, the area of this small square ABCD equals to the length of one side squared. That is to say, it is AP squared. So from the other side, the area of the small square ABCP equals to AP squared. This is the length of side AP squared. And from this equation, AP squared equals to the area of the small square ABCP equals to 36. We derive that AP squared equals to 36. Here we took out all the equation and we found out that the missing side AP equals to the square root of 36, that is 6. So this is side AP. Is equals to 6 units in its length. We know that all the angles inside the square are right angles. So in the small square ABCP, this is a right angle. Therefore, triangle AMP is a right angle. This is triangle AMP, this is a right angle. We know that from one side, the area of this right angle AMP equals to 9 square units in its size according to what is given in the question. But from the other side, the area of this triangle, the right triangle AMP equals to the base AM times the height AP over 2. So again, the area of the right triangle AMP from one side is equal to 9 square units inside according to what is given in the question, but from the other side, the area of triangle AMP equals to the base AM times the height AP over 2. From this equation, we derive that AM times AP over 2 equals to 9. AP is 6, therefore we substitute AP by 6 and found out that 6 times AP over 2 equals to 3. 6 over 2 is 3, so in total this expression equals to 3 times AM equals to 9. Here we divided the equation by 3 and found out that AM equals to 9 over 3, that is 3. So AM, this is side AM, that is equals to 3 units in its length. In the next step, I copied the right triangle AMP in a new page and implemented the Pythagoras theorem on this right triangle AMP. In order to find out the length of the hypotenuse MP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares for the perpendiculars. So here, this is the right triangle AMP that occurs from the original domain. In this right triangle AMP, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AM square plus AP square. MP is the missing side, so leave this it is, and it is equals to AM square. AM is 3, therefore AM square is 3 squared, that is 9, plus AP square. AP is 6, therefore AP square is 6 squared, that is 36. So in total, MP square equals to 9 plus 36, that is 45. So MP square equals to 45. Here we substitute 45 by 9 times 5 and found out actually that MP square equals to 9 times 5. Here we took out all of the equation and found out that MP equals to the square root of 9 is 3, so inside the root we left only with 5. So in total we found out that MP equals to 3 times square root of 5 units in its length. This is slide MP, that equals to 3 times square root of 5 units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rules I mentioned. So in the right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, the 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the small right triangle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the same rule, that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see from the domain that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the figures of the big right triangle A and P are corresponding equal to all the angles of the small right triangle TBM, and therefore those two right triangles are similar to each other according to angle similarity rule. So if you found out that the right triangle A and P is similar, this is the sign of similar to the right triangle T and B according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle A and P, or side TB of the small right triangle T and B equals to side AM of the right big triangle A and P, or side TM of the small right triangle T and B, and it is also equals to side MP of the big right triangle A and P, or side MB of the small right triangle T and B. So if you know that AP over TB equals to AM over TM equals to MP over MB. First of all, we calculated the area of this line segment MB. MB equals to AB minus AM. Yeah, MB equals to AB minus AM. So MB equals to AB. AB 6 because of the fact that all the sides of square ABCD are equal to each other. Each of them is equal to 6 because AB equals to 6. So AB 6 minus MB minus AM, that is 3. So in total, MB equals to 6 minus 3, that is 3. So MB equals to 3 units in its length. MB equals to 3 units in its length. So I should found out that AP over TB equals to AM over TM equals to MP over MB. AP is AP6 over TB. TB is the missing size of relative statistics, and it is equals to AM. AM is 3 over TM. TM is 3. TM is the missing size of relative statistics, and it is equals to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we found out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the denominator, 3 in the denominator, so 3 will get cancelled, and left only with square root of 5. So in total, we found out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two expressions, those two sides are equal to each other, therefore we get the first equation from those two expressions that are equal to each other. That is to say, 3 over TM equals to the square root of 5. Here we multiply this equation by TM, and then we divide it by square root of 5, and finally found out that TM equals to 3 over square root of 5 units in its length. This is the missing side TM is equals to 3 over square root of 5 units in its length. Likewise, those two sides are also equal to each other, therefore we get the second equation from those two sides that are equal to each other. So according to the second equation, we get that 6 over TB equals to the square root of 5. 6 over TB equals to the square root of 5. We will multiply this equation by TB, and then we divide it by square root of 5, and finally found out that TB equals to 6 over square root of 5 units in its length. This is side TB, it is equals to 6 over square root of 5 units in its length. Our test is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of the big square TSQP minus the area of this quadrangle MBCP minus the area of this small right triangle TBM. Repeat again. The area of the green shape in total equals to the area of the big square TSQP minus the area of quadrangle MBCP. This equals to 27 square units inside according to what is given as a question, minus the area on the small right triangle TMB, that the area of the small right triangle TMB. So you have to find out the area of the big square TSQP. The area of this big square TSQP. So first of all, we have to find out the length of one side of the square, that is TP. TP equals to Tm plus MP. Again, TP equals to Tm plus MP. So TP equals to Tm, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. And again, Tm equals to 3 over square root of 5, plus MP. MP equals to 3 times square root of 5. And 3 over square root of 5 plus 3 over square root of 5 plus 3 times square root of 5. We actually multiplied this number by square root of 5 and then we divided by square root of 5 in order to overcome the factor with this number. We should find out that 3 TP equals to 3 over square root of 5, and we have here square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, the amount of this expression we have 15, and we have to divide it by square root of 5. So in total, the length of side TP of the square TSQP is equals to 3 plus 15 is 18 over square root of 5. So TP equals to 18 over square root of 5 units in its length. This is side AP, this equals to, this is side TP, this equals to 18 over square root of 5 units in its length. So TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this green shape, and we only found out that the area of the green shape equals to the area of the big square TSQP minus the area of quadrilateral MBCP minus the area of the small triangle TMB. The area of the big square TSQP equals to the length of one side is the length of side TP squared. So the area of the big square TSQP equals to TP squared minus the area of this quadrilateral and the MBCP. This quadrilateral MBCP equals to 27 square units in size according to what is given in the question. So it is minus 27 minus the area of the right small triangle TMB. The area of the right small triangle TMB equals to the base of the triangle that is TB times the height TM over 2. So again, the area of the small triangle TMB equals to the base TB times the height TM over 2. So the area of the green shape in total equals to the area of the big square TSQP, that is TP square. We already found out that TP equals to 18 over square root of 5, therefore TP square will be equal to 18 over square root of 5 squared minus 27, that is the area of quadrilateral MBCP, minus the area of the right triangle TMB, this equals to TB. TB is 6 over square root of 5 times TM, that is 3 over square root of 5 divided by 2. 18 over square root of 5 squared is 18 squared, that is 324 over square root of 5 squared, that is 5. So in total, the area of the big square TSQP equals to 324 over 5 square units in its size minus 27, that is the area of quadrilateral MBCP minus the area of the right triangle TMB. This equals to 6 times 3 is 18, and square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small right triangle TMB equals to 18 over 10 square units in its size. So in total, the area of the green shape equals to the area of square TSQP, that is 324 over 5. 324 over 5, 64.8 square units in size, minus 27, minus 18 over 10 is minus 1.8. 64.8 minus 1.8 is 63, and 63 minus 27 is 36. So in total, we found out that the area of this green shape is equal to 36 square units in size. So we finish with the first question. In the next step, I present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So the drawing we have square ABCD. We know that one side of square ABCD equals to 10 units in its length. In addition, we know that inside this square ABCD we have this big quarter circle. And also we have this semicircle inside this big square ABCD. We know that the diameter BC of the semicircle is 10. We define the center of this circle, this point as point O. If the diameter is 10, then the radius must be equal to 10 over 2, that is 5. So the radius OB is 5, and the radius OC of this semicircle is also equal to 5 units in its length. Likewise, we have, this is the big quarter circle. Point A is the center of the quarter circle. Point B is the point of the quarter circle itself. Therefore, AB is the radius of the quarter circle, that is 10. AD is also the radius of the quarter circle, that is equal to 10 units in its length. In the next step, we define the intersection point of the quarter circle with this semicircle. This point is point M. Then we join points A and M together by straight line. Point A is the center of the quarter circle, point M is the point of the quarter circle itself, therefore AM is the radius of the quarter circle, that is equal to 10. In the next step, we join points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is equal to 5. AM is tangent to the semicircle at point M. So here we can implement rule 1 because we have the radius OM that is equal to 5, the radius OM of the semicircle that is equal to 5 is drawn to point M, that is the point of tendency of the AM with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent OM will be perpendicular to the radius AM. Then tangent AM will be perpendicular to the radius OM. If AM is perpendicular to OM, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points A and O together by straight line. And we know that all the angles inside square ABCD are right angles, and therefore this is right angle. By joining points A and O, we can do those two right angles. This is the right angle ABO, and this is the right angle AOM. In the next step, we prove that those two right angles can join to each other according to angle similarity rule. That is to say, side BO of the right angle ABO equals to side OM of the right angle AOM. They are both the radii of the semicircle that is equal to 5, and therefore they are equal to each other. In addition, side AB of the right angle AOB equals to side AM of the right angle AOM. They are both the radii of the quarter circle that is equal to 10, and therefore they are equal to each other. And finally, side AO, the common side that belongs to both triangles. So we can write down that AO equals to itself is the common side that belongs to both triangles. So we can prove that all the figures of the right angle ABO corresponding equal to all the figures of this right angle AMO. Therefore, those two right angles can join to each other according to side rule. Again, we should prove that all the three sides of this right angle ABO corresponding equal to all the three sides of this right angle AOM. Therefore, those two right angles can join to each other according to side rule. And for the fact that those two right angles can join to each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can join to each other, and therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. Likewise, from the fact that those two right angles can join to each other, we will derive that those two angles are also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So we know that all the angles inside a triangle, the sum of the angles in a triangle is equal to 180 degrees. So the sum of the angles in the right triangle ABO must be equal to 180 degrees. So which angles we have the right triangle ABO? We have alpha plus beta plus 90 degrees. In total must be equal to 180 degrees. So in the right triangle ABO, the sum of the angles must be equal to 180 degrees. That is to say, alpha plus beta plus 90 degrees in total must be equal to 180 degrees. Here we subtracted 90 degrees from this equation and finally found out that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Here we subtracted alpha from this equation and finally found out that beta equals to 90 degrees minus alpha. So here beta equals to 90 degrees minus alpha. In the next step, I copied the right triangle ABO and in equation implemented the Pythagorean theorem on this right triangle ABO. This is the right triangle ABO, therefore it's from the original drawing. According to the Pythagorean theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so we leave it as it is, and it is equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, AO squared equals to 125, that is 125. AO squared equals to 125. So we substitute 125 by 25 times 5. So AO squared equals to 25 times 5. Here we took out all the equation and I found that AO equals to the square root of 25, that is 5. So inside the root we left only 5. So in total, AO equals to 5 times square root of 5 units inside. This is side AO, this is equals to 5 times square root of 5 units inside. Here we continue to focus on this right line ABO. On the right line ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. So again, in the right line ABO, sinus alpha equals to BO over AO. BO is 5, the opponent's AO is 5 times square root of 5. Again, BO is 5 and AO is 5 times square root of 5. We have 5 denominator and 5 denominator, so 5 get cancelled. We left only with 1 over square root of 5. So in total, we found out that sinus alpha equals to 1 over square root of 5. Our test is to find out the value of angle alpha itself, the size of angle alpha. In order to find out the size of angle alpha, we'll operate the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5. In this way, we get the value of angle alpha itself. Again, so we'll operate the opposite function of sine on, that is arc sine on the result, that is 1 over square root of 5. In this way, we get the value of angle alpha itself. Actually, arc sine 1 over square root of 5 is 26.565. So if you found out that the size of angle alpha is 26.565 degrees in its size. And therefore, 2 alpha equals to 2 times 26.565, that is 53.13 degrees. We already found out that beta equals to 90 degrees minus alpha, therefore beta equals to 90 degrees minus alpha, and alpha equals to 26.565. So beta equals to 90 degrees minus 26.565, that is 63.345 degrees. But again, we found out that the size of angle beta is 63.435 degrees. And therefore 2 beta must be equal to 2 times 63.345, that is 126.87 degrees. So in total, we found out that angle BOM, that is 2 beta equals to 126.87 degrees in its size, and this is angle BOM, that equals to 2 beta and 2 alpha, and 2 alpha equals to 53.13 degrees in its size. Our test is to find out the area of this graph shape. So in order to find out the area of this graph shape, we join points M and B together by a straight line. By joining points M and B, we divided this green shape into 2 parts. We have, this is the first part, it is actually the upper segment BUM, and this is the second part, that is the lower segment MLB. So we'll find out the area of each segment separately, and then we add the 2 areas together, and this will give us the area of this green shape. In order to find out the area of this lower segment MLB, I copied this sector A and B in an equation. We analyze this sector A and B. This is sector A and B, that is according to the original drawing. So, what is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them. This is sector A or B. It is a portion of a circle enclosed by two radii and arc AB between them. And the two radii are defined as the legs of the sector. The angle between the legs of the sector is theta. And the area of this sector, A or B, equals to pi r squared, that is the area of the circle that contains the sector, times angle theta, that is the angle between the legs of the sector, over 360 degrees. Repeat again, a sector is a portion of a circle enclosed by two radii and the arc between them, and the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So we use the new formula in order to find out the area of this sector, sector A and B. Note that this is angle 2 alpha, that is 53.13 degrees. AB equals to AM equals to 10. They are both the radii of the quarter circle, this is equal to 10. So according to the formula that I presented to you, the area of this sector A and B will be equal to pi r squared, that is the area of the circle that contains the sector, times theta, that is 53.13 degrees, over 360 degrees. R is 10, therefore r squared is 10 squared, that is 100, so pi r squared is 100 pi, times 53.13 over 360 degrees. Actually, the value of this expression in total, 100 pi times 53.13 over 360 degrees, is equal to 46.3646 cubes in size. So in total, we found out that the area of this sector A and B is equal to 46.4636 cubes in size. Our task is to find out the area of this lower segment MLB. This is the lower segment MLB. We have to find out the area of this lower segment MLB. So, what is the area of the lower segment MLB? From the drawing, it is very easy to see that the area of this lower segment MLB will be equal to the area of sector A and B minus the area of triangle A and B. It is very easy to see that if you remove from this sector A and B this triangle A and B, we will get segment MLB. Therefore, the area of this segment B and M equals to the area of sector A and B. We already found out that the area of sector A and B equals to 46.3646 cubes in size, minus the area of triangle A and B. This is triangle A and B. In order to find out the area of this triangle A and B, I presented to you a new formula that will help us to find out the area of any triangle. Okay. This is triangle ABC, that could be any triangle. This triangle ABC, side AB equals to A unit in itself, side AC equals to B unit in itself, and the angle between side AB and side AC is theta. So, the area of this triangle ABC, that could be any triangle, equals to A times B times sinus theta over 2. But again, the area of this triangle ABC, that could be any triangle, equals to A times B, that is the multiplication of the two sides by each other, times the angle, times sinus the angle between those two sides, that is sinus theta over 2. So we use the new formula in order to find out the area of this triangle, triangle ABM. According to the new formula that I presented to, the area of this triangle ABM will be equal to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between the two sides, that is 53.13 over 2. So the area of this triangle ABM equals to AB times AM times sinus 53.13 degrees over 2. AB is 10, AM is also 10, so AB times AM is 10 times 10, that is 100. Sinus 53.13 degrees is 0.8 divided by 2. 100 over 2 is 50, 50 times 0.8 is 40. So in total, we found out that the area of this triangle ABM is equal to 40 squares in size. So in total, the area of this lower segment BM equals to the area of sector ABM, that is 46.3646, minus the area of the triangle ABM, that is 40. 46.3646 minus 40 is 6.3646 squares in size. So in total, we found out that the area of this lower segment BLM is equal to 6.3646 square units in size. In the next step, found out the area of the upper segment BOM. So I copy sector BOM in an Olympiad and analyze this sector BOM in order to find out the area of this segment BUM, the upper segment BUM. Actually, this is sector BOM that I call it from the original drawing. The two legs of the sector OB and OM, they are both the radius of the semicircle is equal to 5. The angle between the two legs of the sector is 2 beta, that is 126.87 degrees. So according to the formula that I presented to you a couple of minutes ago, the area of the sector BOM will be equal to pi r square, that is the area of the circle that contains the sector, times theta, that is 126.87 degrees over 360 degrees. R is 5, therefore r square is 5 squared, that is 25, so in total pi r square is 25 pi, times 126.87 degrees over 360 degrees. So in total, the value of this expression 25 pi times 126.87 degrees over 360 degrees, in total is equal to 27.678 square units in size. So in total, we actually found out that the area of this sector AOM equals to 27.678 square units in size. Our test is to find out the area of this upper segment VOM. So what is the area of this upper segment VOM? The area of this upper segment VOM equals to the area of sector BOM minus the area of triangle BOM. It is very easy to see from the drawing that if you remove from this sector BOM this triangle BOM, we get segment BUM. And therefore, the area of segment BUM equals to the area of sector BOM minus the area of triangle BOM. We already found out that the area of sector BOM equals to 27.678 square units in size minus the area of triangle BOM. We use the new formula in order to find out the area of this triangle BOM. According to the new formula, the area of this triangle BOM will be equal to BO times OM times the angle between the two sides, times the angle between the two sides, that is 126.87 degrees over 2. But again, the area of this triangle BOM in total equals to BO times OM times the angle between the two sides, that is 126.87 degrees over 2. BO equals to 10, OM also equals to 10, and therefore BO equals to 5, OM also equals to 5, above the radius of the semicircle is equals to 5. So BO times OM is 5 times 5, that is 25. Sinus 126.87 degrees is 0.8 divided by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So we found out that the area of this triangle BOM equals to 10 square units in size. So in total, the area of this upper segment BOM equals to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10. 27.678 minus 10 is 17.678 square units in size. So in total, we found out that the area of this upper segment BOM equals to 17.678 square units in size, and we only found out that the area of the lower segment MLB is equal to 6.3646 square units in size. And therefore, the area of this green shape will be equal to the area of the upper segment BOM, that is 17.678 square units in size, plus the area of the lower segment and MLB, that is 6.3646 square units in size. 17.678 plus 6.3646, in total it is equal to 24.0426 square units in size. So we found out that the area that we are looking for this question, that is the area of this green shape, in total it is equal to 24.0426 square units in size. Okay, thank you very much.